Okay, year 12, here we go with forces 2, the last one. It's hard to believe that we've finally come to the end of all these. I've got to say, you've been great getting them all done, so well done. Here we go, let's finish it off then. So we're going to add all these up to get the resultant of the forces. So we've got 2i plus 4j plus 6i minus 14j plus 3i plus 2j, and altogether that gives us 11i minus 8j. Now if we're going to have a fourth force acting on it to keep it in equilibrium, it would have to cancel out this force exactly. And how will it do that? By being 11i plus 8j, just being the negative of what we've got there. Okay, on to question 2. So if we're going to have this, we've got a force diagram for just the top block. So let's draw ourselves a little rectangle. Here we go, and we can see that we have clearly got, because we're in equilibrium, we've clearly got a force acting up, and we're going to have a force acting down as well. Arrow's better there. Okay, there we go. Okay, so what's acting down? Well, all that can be acting down is the weight of it, which must be 5g, or that's going to be 5 times 10 because we're using g equals 10, so that's 50 newtons. Now it's not moving, so you must be having the normal reaction acting up, so a normal reaction of 50 newtons acting back up. Now if you've got the lower shape here, the lower box, let's draw that one. Now this time you're going to have two forces acting on it. You've got its own weight, and you've also got the weight of the box on the top, and then this will be counterbalanced by just a normal reaction from the ground. So acting down, you've got its own weight, which is going to be 70 newtons, and the weight of the other box, which will be 50 newtons, and therefore that must be countered by a normal reaction of 120 newtons. Okay, so for question 3, we're now going to have a person mass 70 kilograms standing in the lift. So there's a person, and here's a lift, and there's all that can be acting is their own weight will be acting down, and there'll be a normal reaction acting up from the floor of the lift. That's the only forces that can be in play here. So the person weighs of mass 70 kilograms, there must weigh 70g, and there's going to be a normal reaction acting up. And the other thing that we're told, first of all, this lift is accelerating upwards of 4 meters per second, I should say squared, rather than AQA. So that's probably not going to be a lift that you're going to find in your local department store. Far more likely to be in a theme park, I would imagine, going up like that. Anyway, r minus 70g equal to 70 times force. This is just from F equals ma, equation of motion, because our force, our resultant force it's going up, so we can have the r being positive as in the force being positive, and there we go. And so r is going to have to be 70 times 4 plus 70 times 9.8, and so that will give us 966 newtons. Okay, now if the lift were accelerating downwards, it's an even more hair-raising 6 meters per second squared. There we go, and right, there we go. And so again, we've got our forces here. We've got the weight of the person in the lift, which is 70g, and we've got a normal reaction which is acting up from the floor of the lift. Just move that down to the floor of the lift. There we go. Okay, so 70g again here, normal reaction there, but this time we're accelerating down at 6 meters per second squared. So this time the equation of motion, the F is equal to ma, is going to be 70g minus r is going to be equal to the mass, which is 70, times the acceleration, which is 6. So it kind of reverses around, so R is going to be equal to 70 times 9.8 minus 70 times 6, which gives us simply 266 newtons, so a lot less than previously. Okay, right, question 4. Now, here's the question, and just scroll that down. So we've got a few little bits to do, so I'm going to do them each in turn. So here's our 5 kilogram box, so that's going to have tension, I want to call it tension 1 acting up on it, because we've got 2 strings here and we've got to find the tension in each of them. So tension 1 is acting up, and obviously the weight of the box will be acting down. So again, we're just going to use F is equal to MA, and because it's accelerating down, because we're told in this part of the question that the box moves to the left. Yeah, the box moves to the left, says that there. So the 5, so if that goes to the left, that one's going down. So F is equal to MA, so that means that 5G minus T1 is equal to 5 times 1.96. And so if we just spin that around, we get T1 is going to be equal to 5 times 9.8 minus 5 times 1.96, which gives us 39.2 newtons. Okay, the next bit is to resolve horizontally on the 8 kilogram box. So we know for this one that T1 is going this way, and as we said before, T2 will be in the other string, and that is going to have to act to the right, because as we can see, if we just pop back here, there's another box here pulling down. So the tension, there will be a tension acting, trying to pull the box to the right, even though it doesn't end up moving that way. Obviously it's a string, so tension can only act in that direction. It can't act with the T1, or it would not be, or if there wouldn't be tension. So putting that all together, that gives us T1 minus T2 is equal to mass, which is 8, times by the acceleration. Sorry, we've just got T1 minus T2 is equal to MA, and so we've got 39.2 that we just worked out, minus T2 is equal to 8 times 1.96, and so T2 is going to be 39.2 minus 8 times 1.96, and so that gives us 24 newtons. Right, okay, now C. I diverge from what AQA say on this, but I am right and they're not. So T2 will be acting up on this box, and mg will be acting down. So T2 minus mg, we know that it's going up, is going to be equal to ma. We know it's going up because the box here was moving to the left, and so if that's going down, that's going to the left, this one's going up. So the T2 will be overwhelming the weight. So T2 minus mg is equal to ma. So that will become 24 minus 9.8 m is equal to 1.96 m. So 24 is equal to 11.76 m, and m must therefore be equal to 24 over 11.76, which gives you 2.04 kilograms. Okay, moving on to question 5. So here we've got a 2 trucks, they're like trailers I guess, and you've got a train there, so sort of some kind of American stuff talking about trucks and engines, but anyway, these 4 kilograms and 3 kilograms, there's no power in those, that's why they're called trucks. And in the engine here, this one does have power, so this one will try to move it off to the right. Okay, so if we just put all this together, we're going to have an overall force. I'm going to treat it all as one particle in part A. Okay, so the overall thing, we've got a 300 Newton resistance there. We're obviously going to have tensions acting there. We're going to have a we're going to have 150 newtons acting there, and we've got another resistance of 100 newtons acting here, and we're going to have tension acting both ways there. We'll call that T2. Okay, so we've got here F is equal to MA, and so I've got 18550 minus all of my resistances. The total mass of the whole thing is 12m, and the acceleration of the whole thing is 2.5. So just from moving all that around, solving that equation gives me m is equal to 600 kilograms. Okay. Right, moving on to part B, we've got to find the tension in the horizontal coupling between the trucks and between the 4 kilogram truck and the trailer. So starting off, we're looking at the truck here. We've got the 300 Newton resistance force, and we've got what we call T1 acting there. So that means if I just use F is equal to MA because it's accelerating, I've got my 18550, which is the truck, which is the driving force of the engine, and opposing it I've got 300 newtons, and I've got T1. Don't really need to put the newtons there. And that's going to be equal to mass times acceleration, or 3000, because I knew that m was 600 now. So 5m must be 3000, sorry, times by 2.5, and so just searching that out gives me T1 is equal to 10,750 newtons. For the other one, I've got T2. So I'm just looking at the last truck here because it's just a little bit easier to just look at the end ones rather than the middle one. And I've got 1800 there. Because m is 600, I've got that is 1800 there. So here F is equal to MA. So I've got T2 minus 100 is equal to 1800 times by 2.5, and so T2 works out to be 4,600 newtons. There we go. Alright, question 6, a little bit tricky. We'll just take a moment just to draw this out. Right, okay, so at this moment that's the situation is. So we need to add some forces onto this. Now as it is everything is smooth, it's a smooth horizontal tab, a smooth pulley, so friction we don't worry about, not until year 13. We are going to have tension, which will act equal and opposite in the string, and there's going to be a weight down here of 3g. Okay, so we can now look at the forces on each box in turn. So if we look at the 3 kilogram box, that will give us, again from F equals MA, 3g minus T is equal to 3a. If we look at the 9 kilogram box, that gives us T is equal to 9a. So if we just simply add those two simultaneous equations together, that gives us 3g is equal to 12a, and so a must be 3 times 9.8 divided by 12, which gives us 2.45 meters per second squared. Okay, and then if we can just go back into the equation up here for the 9 kilogram box, call that star, then T will be 9 times 2.45, which gives us 22.05 newtons. But we're not done yet, because we have got to find the time it takes the boxes to move 3 meters. That's a table of immense proportions. So we want to find the time it takes to move 3 meters. So S will be 3 meters, U will be 0 because they're released from rest, V we don't know or care about, A is going to be 2.45, and time is what we're trying to find. So this means we've got to use S is equal to UT plus 1/2 AT squared, and so 3 is equal to 0 times T plus 1/2 times 2.45 times T squared. So T will be equal to the square root of 3 over 1/2 times 2.45, and that works out to be 1.56 seconds. Right, okay, question 7. This is quite a big one. And I really think that we just need to just reinterpret the question before we begin, just to make things nice and clear. So I'm just going to draw this out. I'll be back to you in a moment. Right, okay, so here is the situation as I've drawn out there. Let me just add the forces to it. So quite simply, we're just going to have tension acting in this string, and we're going to have the weights of these particles, so 6g pulling down on that and 3g pulling down on that. Now here's what's going to happen. The system will be released from rest, and what's going to happen is that this one, the 6 kilogram particle, is going to descend. That's going to go down, and the 3 kilogram particle is going to go up. But there's only 2 meters here, and clearly we've got a 3 meter distance between where they are now and the pulley. So once this 6 kilogram particle has gone down 2 meters, it will hit the ground, and then the string will go slack. Now the 3 kilogram one will still be moving up at this point. It will still have some momentum and some velocity moving upwards, and the question is it going to hit the pulley? Will this 3 kilogram mass bump this pulley, or will it just go up and not quite get there and then just fall down again? So that's what we're after. So if we just form some equations of motion, again using F equals ma, we know the 6g is going to overwhelm the 3g and indeed overwhelm the tension. So 6g minus t will be equal to 6a, and on the other one, t minus 3g will be equal to 3a. Then just adding those two together gives us 3g is equal to 9a, and so a is equal to 1/3 of g, or 3.27 meters per second squared. Okay, so the 3 kilogram mass is going to accelerate up for 2 meters at 3.2 meters per second. So we need to find out how fast it's going to be going at the top of that. So for this one, we would just use suvat. I haven't put this on here. So s is equal to 2. U is equal to 0 as it's released from rest. V is what we're trying to find, so that's question mark. A is going to be the 3.27 that we just worked out, and time is inconsequential. So that must be V squared is equal to U squared plus 2AS, and so V squared will be equal to 2 times 3.27 times by another 2, and that will give us that V comes out to be 3.62 meters per second to the minus 1. So it's going at 3.2 meters per second. So now we've got to the point where this 3 kilogram mass has moved up here. It's now here, and it's not accelerating anymore, but it's still moving up at 3.62 meters per second. So is it going to be able to make the extra 1 meter to reach the pulley? So in order to do that, we need to use V squared equals U squared plus 2AS again. So S is equal to question mark, so we're trying to find that. U is now its initial velocity is just now the final velocity that we worked out, 3.62. V is going to be 0 because it's going to stop at some point. A is going to be minus 9.81 because gravity is opposing this motion, and T is question mark because we don't really care. And so we've got V squared is equal to U squared plus 2AS again. So 0 squared is equal to 3.62 squared plus 2 times minus 9.81 times by S. That gives us S is 2/3. And so the answer is no. The 3 kilogram mass will not reach the pulley. And if we can see, that does answer our initial question. Will it reach the pulley? No, it won't. And that's it.